We'll start in about 1 minute. Today we'll start section 8.1 on arc length, or the length of a curve. To begin with, we'll recall the mean value theorem from section 4.2. Let f of x be a continuous function on a closed interval from a to b, and differentiable on the open interval from a to b. Then the mean value theorem says there is a number c where a is less than c, which is less than b, such that f prime of c equals f of b minus f of a divided by b minus a. So I'll draw a little picture to illustrate the mean value theorem. So suppose we have some function y equals f of x, and then on the interval from a to b corresponds 2 points on the graph. So the ordered pair for this point on the left is a f of a, and the ordered pair for the point on the right is b f of b. If you draw a straight line through those 2 points on the graph and compute the slope of that line, this is, you might recall, this is referred to as a secant line. And the slope of the secant line, I'll use m for slope and then put sub secant. We just apply the slope formula that for the slope of the line that passes through those 2 points. So y1 minus y2 in this case is f of b minus f of a divided by x1 minus x2, which is b minus a. So that's just the slope of a tangent line. Well, the mean value theorem says if you have a continuous function f that's differentiable, then there exists some number c in the interval from a to b. And a point on the curve that corresponds to that, this point is c f of c. But the slope of the tangent line that passes through that point is f prime of c. So the slope of the tangent is f prime of c. So I attempted to make it look like the two lines have the same slope, and that's what the mean value theorem says. There is a number between a and b at which the derivative is equal to the average rate of change. Okay, we will use the mean value theorem shortly. So now let's let y be equal to f of x be a function such that the first derivative of f is continuous for all x on an interval from a to b. And we're going to derive the arc length formula, which is, in this setting, it's the length of the curve y equals f of x on the interval from a to b. So if you just look at this picture up here, what we're going to do is derive a formula for finding the arc length of the length of the curve of the function f between domain values a and b. Okay, so what we are going to do, we're going to subdivide the interval from a to b into n subintervals. And then on each of the subintervals, we're going to approximate the length of the curve. So if we have some graph of a function y equals f of x from a to b, say, the last endpoint is x of n. And the first endpoint, which corresponds to a, is x of 0. And we subdivide this interval from a to b into n subintervals. And each subinterval has a length delta x, which can be computed by dividing b minus a by n, because we have n subintervals. Okay, we'll just focus on one of the subintervals. We'll refer to it as the ith subinterval. So from x of I minus 1 to x of I, and corresponding to those 2 points are the ordered pairs x of I minus 1 and f of x of I minus 1 on the graph. The other point is x of I and f of x of I. So an approximation for the length of the curve on this interval is the length of the line segment that connects those 2 points. So I'll refer to the arc length on this interval as L sub I for the arc length on that subinterval from x sub I minus 1 to x sub I. And we can approximate that arc length on that interval just by computing the distance between those 2 points using the distance formula. So L sub I is approximately equal to using the distance formula, the square root of the quantity x sub I minus x sub I minus 1 squared plus the quantity f of x sub I minus f of x sub I minus 1 quantity squared. That's just the distance formula applied to those 2 points with those coordinates. Okay, we're going to multiply L sub I by 1. And the form that 1 takes is delta x divided by delta x, where delta x is the length of each subinterval. And make a note that delta x is equal to x sub I minus x sub I minus 1, because it's the length of each subinterval. Okay, so I couldn't see that for a second. We're just multiplying this approximation of the length of the curve using the distance formula. Then we multiply by 1 in the form delta x over delta x. Okay, the delta x in the numerator, we're going to keep that on the outside of the square root. But when we put delta x on the inside, we change it to the quantity delta x squared if it's inside the square root. So I'll do that in this next step. So we have L sub I is approximately equal to, then x sub I minus x sub I minus 1 quantity squared divided by delta x squared, and then plus f of x sub I minus f of x sub I minus 1 quantity squared divided by the quantity delta x squared, and then multiplied by delta x. Well, delta x is just x sub I minus x sub I minus 1. So this term on the left is going to simplify to 1. So L sub I is approximately equal to the square root. This term is 1. And the term on the right, we're also going to replace delta x with x sub I minus x sub I minus 1. But we have a quantity squared in the numerator divided by a quantity squared in the denominator. And we can write that as a single rational expression squared. So in the numerator, we have f of x sub I minus f of x sub I minus 1. And we're dividing by delta x, but delta x is just x sub I minus x sub I minus 1. And then we square the entire rational expression. And then remember, we still have a delta x on the outside. Okay, so this bottom line right here is just what we get when we simplify the line above it inside the square root. Okay, now we apply the mean value theorem. Notice inside the square root, inside the brackets, we have the average rate of change of that interval from x sub I minus 1 to x sub I. In other words, inside the bracket, we have the slope of the line that connects those 2 points on the graph of f of x. So according to the mean value theorem, there is a point in the interval from x sub I minus 1 to x sub I. I'll just write there exists x sub I star such that f prime of x sub I star is equal to the average rate of change, f of x sub I minus f of x sub I minus 1 divided by x sub I minus x sub I minus 1. This x sub I star is in the interval from x sub I minus 1 to x sub I. So I should indicate that here. This is an element, or it's inside the set of numbers from x sub I minus 1 to x sub I. It's in that interval. So we can simplify this approximation of the arc length on that interval. L sub I is approximately equal to the square root of 1 plus, and then the derivative f prime evaluated at x sub I star quantity squared, and then delta x. We can make an approximation like this on all n subintervals. This is just one of the subintervals. And so the length of the curve of y equals f of x on the interval from a to b, I'll refer to that as capital L. And we're just going to add up the individual approximations. So the length is approximately equal to a sum starting with I equals 1 and going to n. And each of the n terms has the form the square root of 1 plus f prime of x sub I star quantity squared, square root of that, times delta x. Okay, this is a Riemann sum. We're just adding n terms. And you might agree, if you look at this picture, that as n increases, our approximations for the curve, the length of the curve, get better and better. The more subintervals we have, the better our approximation is of the length of the curve. So if we let n go to infinity, I'll make a note of that. Well, I might as well just write it. So the actual exact arc length, L, is equal to the limit as n approaches infinity of the Riemann sum. And the limit is a definite integral. The definite integral from x equals a to b of the square root of 1 plus f prime of x squared dx. So this is our arc length formula. So it's probably a good idea to memorize this arc length formula. But if you forget it, you can always derive it, like by going through the steps that we just did. Okay, on the next page, we formally state the arc length formula, and then we'll do a few examples. Okay, the arc length formula, if the derivative of f is continuous on the closed interval from a to b, the length of the curve y equals f of x for values of x between a and b is given by L equals the definite integral from a to b of the square root of 1 plus f prime of x squared dx. Using Leibniz notation, so remember if y is equal to f of x, the Leibniz notation for the derivative is dy dx. So you can use the Leibniz notation if you want. Okay, so here's our first example. Find the length of the curve f of x equals x to the third over 3 plus 1 over 4x, where the values of x range from 1 to 2. So I'll give you a couple of minutes, see what you come up with for the length of the curve for this function f on the interval from 1 to 2. I'll go ahead and start it. You can keep working on it and try to ignore me if you want. We do need to know what the derivative is. So f prime of x is x squared, and then minus 1 over 4x to the second. And we're going to have to square this quantity and then add 1 to it and put it inside the square root, and then integrate it from x equals 1 to x equals 2. So since I have to square this quantity, and one of the terms is a rational expression, writing it as a single rational expression with a common denominator seems a little more convenient. So the least common denominator is 4x squared, so we get 4x to the fourth minus 1 divided by 4x to the second. And let's go ahead and square this. So we're going to square the derivative. So I'll do half of it. When we square the denominator, we get 16x to the fourth in the denominator. And you do the other half in the numerator. Okay, in the numerator, when we square the quantity 4x to the fourth minus 1, we're going to get 16x to the eighth minus 4x to the fourth minus 4x to the fourth a second time, and then plus 1. So altogether, in the numerator, 16x to the eighth minus 8x to the fourth plus 1. Okay, then we're going to add 1 to this, and then put that inside the square root. So in the next line, f prime of x squared plus 1 . So I'll rewrite the 16x to the eighth minus 8x to the fourth plus 1 over 16x to the fourth. And since I'm adding 1, I'm going to want to write the final result as a single rational expression with a denominator of 16 times x to the fourth. So in this step, I'm going to go ahead and write 1 in the form 16x to the fourth over 16x to the fourth. And then we have a common denominator of 16x to the fourth. And then we can add the two numerators. When we add the numerators, we have 16x to the eighth, and then minus 8x to the fourth plus 16x to the fourth is plus 8x to the fourth, and then plus 1. Okay, is there any nice feature about this expression that you notice? Since we have to put it inside the square root, well, it has a nice feature for being inside of a square root. The numerator is a perfect square, and so is the denominator. So I'll go ahead and write this as a quantity squared. The numerator is 16x to the eighth plus 8x to the fourth plus 1. That's the same as 4x to the fourth plus 1 quantity squared. So 4x to the fourth plus 1. I'm going to put the squared on the outside of the parentheses. The denominator is also a perfect square. If you square the term 4x to the second, you get 16x to the fourth. Well, I'll go ahead and write a little bit in a little bit more detail than is absolutely necessary. But the length of the curve from x equals 1 to 2 is the square root of this quantity 4x to the fourth plus 1 over 4x to the second quantity squared dx. But when we take the square root of a perfect square, we just get we're just going to get 4x to the fourth plus 1 over 4x to the second. dx. Since we're dividing by a single rational or a single term in the denominator, we can write this as a sum of two rational expressions, or the sum of two terms. 4x to the fourth divided by 4x to the second simplifies to x to the second, and then plus 1 divided by 4x to the second. But for convenience, I'm going to write it as plus 1/4 times x to the negative 2. And we can easily find an antiderivative for x squared plus 1/4 x to the negative 2. Okay, an antiderivative for x to the second is x to the third over 3. And an antiderivative of x to the negative 2, if you isolate that, that's x to the negative 1 divided by negative 1. So this will simplify to minus 1 over 4x. And then we evaluate this from x equals 1 to x equals 2. Okay, so we get L equals, first replace x with 2. 2 to the third over 3 is 8/3. Minus 1 over 4 times 2 is minus 1/8. And then we subtract the quantity we get when we replace x with 1. So minus the quantity 1/3 minus 1/4. And we'll do a little bit more arithmetic. 8/3 minus 1/3 is 7/3. And minus 1/8 minus negative 1/4 is plus 1/8. And then a common denominator of 24. And 7 times 8 is 56. And 1 times 3 is 3. So the arc length is 59/24. So almost 2.5 units. Okay, let's do the next example on the next page. Find the length of the curve g of x equals the natural log of secant of x for values of x between 0 and pi over 4. We need to know what the derivative is, g prime of x. What's the derivative of the natural log of secant of x? The natural log of the secant of x is a composition of functions, so it involves the chain rule. So as a reminder, I'll replace over here on the side, and instead of g of x, I'm going to write y equals, and then replace secant of x with u. So y equals the natural log of u, where u is equal to secant of x. And we want to find dy dx. So by the chain rule, dy dx is dy du times du dx. Okay, if y equals the natural log of u, what's the derivative of y with respect to u? One over u, right? And if u equals secant of x, the derivative of u with respect to x, so the derivative of secant of x is secant of x times tangent of x. And then we replace u with secant of x again, so I might as well just write it over here. G prime of x is 1 over secant of x times secant of x tangent of x, or we can write it as secant of x times tangent of x over secant of x, and that simplifies to tangent of x. Okay, if you need to review the chain rule, then you can look in the textbook in the Calculus 1, I forget which section that's in, but you can look up the chain rule in the index if you need to review that. Okay, so we can write down using the arc length formula. The length of the arc is the definite integral from x equals 0 to pi over 4 of the square root of 1 plus the square of the derivative. So the derivative is tangent of x, so we square that, tangent of x squared. And now we're in familiar territory. So what should we do now? Yeah, online I see cosine of x times secant of x times tangent of x. That's true, but cosecant of x times secant of x is 1. So that simplifies to tangent of x also. Okay, what about this? What can we do with this integrand, the square root of 1 plus tangent of x squared? One plus tangent of x squared is secant of x squared. So we can write this as L equals the definite integral from 0 to pi over 4 of the square root of secant of x squared dx. Secant of x is positive on the interval from 0 to pi over 4, so the square root of secant of x squared is just secant of x. And then an antiderivative for secant of x. And antiderivative for secant of x is the natural log of the absolute value of secant of x plus tangent of x. And we want to evaluate this from 0 to pi over 4. Okay, so first, replace x with pi over 4. We have the natural log of secant of pi over 4 plus tangent of pi over 4. And then minus the natural log of secant of 0 plus tangent of 0. Secant of pi over 4 is the reciprocal of cosine of pi over 4. Cosine of pi over 4 is 1 over the square root of 2. So that means secant of pi over 4 is the square root of 2. Tangent of pi over 4 is 1. Secant of 0 is 1, tangent of 0 is 0. The natural log of 1 is 0. So this is going to simplify to the natural log of the quantity square root of 2 plus 1. So that's the arc length. Hey, there's 1 or 2 problems that I assign for practice where x is defined as a function of y, but don't let that fool you. So in the event that x equals g of y, if that's a continuous function for values of y between c and d and differentiable on the interval, open interval from c to d, then the length of the curve from the points g of c, c to g of d, d is this formula. It's completely analogous to the arc length formula that we derived, where y is a function of x. It's just that in this case, x is a function of y, but it's essentially the same formula. Another item in this section is the arc length function. So we can define an arc length function just by using the arc length formula. But here's a brief definition of the arc length function. An arc length function measures the arc length of a curve from a specified starting point on a curve to any other point on the curve. So if we let f of x be a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b, and then if we let the function s of x be the function that measures the arc length from the initial point a f of a to another point x f of x on the curve where the values of x are between a and b, then the arc length function s of x is the definite integral from a to x of the square root of 1 plus f prime of t squared dt. The reason that we're using a different variable t is because x already has another meaning. X represents a number that's between a and b, and so the function f cannot be a function of x in this setting. So you don't have to use t, just make sure that the variable that you use is not x. And then the fundamental theorem part 1. You might remember from calculus 1, if you have a function f of x defined as a definite integral from a to x of some function of t, then s prime of x is just the function in the integrand with the variable t replaced with x. So this is the fundamental theorem of calculus part 1. So if necessary, go back to Calc 1 and review this. Okay, let's look at our next example. So on this one, we're going to find the arc length function for a curve y equals the natural log of sine of x. For values of x that are strictly between 0 and pi. And the starting point for this arc length function is the the ordered pair pi over 2, 0. Okay, we need to know how to find the arc length, and then we'll use that to define the arc length function. So we need to find the derivative of y with respect to x. So here we can use the chain rule. Well, we are going to use the chain rule. How much of that you write down is sort of dependent. But this is similar to what we saw earlier. The derivative of sine of x is cosine of x, so that goes in the numerator, cosine of x, and sine of x goes in the denominator. But cosine of x divided by sine of x is cotangent of x. And the arc length function is going to be the definite integral. Let's see, x starts at pi over 2. And I'm sorry, I should have written s of x. So pi over the limits are from pi over 2 to x. And then we have to figure out what goes inside the square root. It will have the form 1 plus dy dt squared dt. Okay, so we know what dy dx is. That's cotangent of x. So when we square dy dx, we get cotangent of x squared. So let's go ahead and write the arc length formula. We won't worry about the limits right now, but this is going to be the square root of 1 plus cotangent of x squared dx. And 1 plus cotangent of x squared cosecant of x squared and the square root of cosecant of x squared is cosecant of x. And then finally, the antiderivative of cosecant of x. So this antiderivative is the natural log of the absolute value of cosecant of x minus cotangent of x. Okay, so in our arc length function, we could go to this step right here, cosecant of t dt. And then we have the natural log of the absolute value of cosecant of t minus cotangent of t, evaluated from pi over 2 to x. Okay, so we're almost done with this one. The upper limit is x, so replace t with x. We get the natural log of the absolute value of cosecant of x minus cotangent of x, and then minus the natural log of the absolute value of cosecant of pi over 2 minus cotangent of pi over 2. Cosecant of pi over 2 is the reciprocal of sine of pi over 2. Sine of pi over 2 is 1, so cosecant of pi over 2 is 1. What about cotangent of pi over 2? Well, cotangent of pi over 2 is equal to cosine of pi over 2 divided by sine of pi over 2, or 0 divided by 1. So this natural log over here on the right is the natural log of 1, but the natural log of 1 is 0. So the only survivors for the arc length function f of x is the natural log of the absolute value of cosecant of x minus cotangent of x. And this is defined only for x values that are between 0 and pi, but excluding the endpoints. Oops. 0 less than x, which is less than pi. Okay, we're out of time for today. Tomorrow we'll do this last problem, and then we'll move on to section 8.2. So online, go ahead and sign in for attendance.